If you asked a standard computer to chart out, every single structural way to organize just 15 items, standard memory mapping would probably crash your machine in a matter of seconds.
Oh, absolutely. It's just too much.
Right. The sheer volume of data, like the historical memory of where the computer's been, tracking every possible branch, it just becomes this gargantuan weight.
Yeah, the RAM just fills up instantly.
Exactly. Yet in 2019, mathematicians found a way to map out over 155 million structural variations in about 2 minutes. And they did it using less memory than like a single open tab on your web browser.
Which is still just mind-boggling to think about.
It really is. And how do they do it? Basically, by abandoning the entire concept of memory altogether.
Just throwing it out the window.
Yeah. So welcome to today's deep dive. We are looking at a really fascinating 2026 presentation by the researcher at LUK036. It's titled Gray Code Ordering, From Binary Strings to Rectangulations.
It's a fantastic paper. We're essentially tracing this remarkable evolution. What begins as a very practical workaround for the physical constraints of early clunky hardware.
Like really old school machines.
Right, exactly. It transforms into this absolute masterclass in abstract geometry and high-level algorithmic efficiency.
And if you've ever felt overwhelmed by how your own devices track just mind-boggling amounts of data without instantly crashing, well, the secret isn't always just a bigger engine or more RAM.
No, it's often much more elegant than that.
Right. It often lies in this memory-saving concept we're going to explore. Okay, let's unpack this. To really understand how a computer can juggle millions of variables without remembering its own past, we have to start back in 1953.
At Bell Labs.
Yes, Bell Labs, with a researcher named Frank Gray.
Right. So at that time, engineers were really wrestling with analog to digital conversion. They were trying to take a continuous physical signal like a sound wave or maybe a voltage reading and convert it into a digital binary code.
Which is just sequences of zeros and ones, right?
Exactly, just zeros and ones. But the massive roadblock they kept hitting was transition errors. Because in standard binary counting, transitioning from the number 3 to the number 4 requires you to go from the binary sequence 011 to 100.
So to get from 3 to 4, 3 entirely different digital switches have to physically flip their state at the exact same millisecond.
Yes. The 0 becomes a 1, the first one becomes a 0, and the second one becomes a 0.
And in physical, real-world hardware, getting perfect instantaneous synchronization across multiple switches is just, well, it's impossible.
It really is. If one switch flips even a fraction of a millisecond faster than the others, your system might briefly read 001 or maybe 111 before finally settling on the correct number.
Oh, so you get these wild, incorrect, intermediate spikes that just corrupt the whole data stream.
Exactly. It creates chaos. So Frank Gray's solution was to completely reorganize how the numbers were ordered in the first place. He created a sequence where successive binary values differ in exactly one single bit position.
I like to think of it like a massive combination lock. Like, imagine you have to hit every possible combination to open a giant safe, but the mechanical rules of the safe dictate you can only ever turn one single dial, exactly one notch at each step.
That's a great way to visualize it. You are physically barred from spinning 3 dials at once.
Right, so in Frank Gray's sequence, the number 3 is 010, and the number 4 is 110. Only that very first bit changes. There's no chaos and absolutely no intermediate spikes.
What's fascinating here is that this minimal change constraint doesn't just fix a hardware bug. It minimizes physical errors by ensuring minimal state change, yes.
Oh.
But the specific version they developed, known as the Binary Reflected Gray Code, or BRGC, it revealed incredibly powerful mathematical properties.
Properties that went way beyond just fixing old hardware.
Beyond. First off, the sequence is cyclic. When you reach the very last combination in the entire sequence, you find that you are exactly 1 bit flip away from your starting value.
Oh, wow. So it forms a perfect closed loop, which means it's complete. And the source material actually points out that this makes it a perfect Hamilton cycle.
Yes, a very important concept.
For anyone who hasn't encountered that term, a Hamilton cycle is a concept from graph theory. It's basically where a path visits every single possible state or vertex exactly once, without ever repeating, before arriving right back at the start.
And that completeness is crucial. The BRGC hits every possible binary combination once and only once. And it achieves this through recursion.
Wait, how does the recursion work here?
Well, you build a larger gray code by taking a smaller one, creating a mirrored reflection of it, and then attaching a 0 to the first half and a 1 to the reflected half.
Huh. So it's just this incredibly elegant mirror and prefix construction.
Right, and it scales up infinitely while always preserving that strict one change at a time rule.
That's amazing. And once computer scientists realized the raw mathematical power of this minimal change rule, they obviously didn't want to leave it trapped in just simple binary code.
No, they immediately saw the broader potential.
Yeah, they started looking at all the other complex data structures they had to manage. Like, if changing one thing at a time works so perfectly for zeros and ones, could that same logic be applied to organize other kinds of chaos?
And that brings us out of basic binary strings and into the realm of permutations and combinations.
Right. And the logic scaled up remarkably well. Researchers began applying gray code principles to permutations. For a quick refresher, a permutation is simply an arrangement of all members of a set into a specific sequence or order.
Right. If you have the letters A, B, and C, figuring out all the ways to order them, like ABC, ACB, BAC, and so on, that's generating permutations.
And the source highlights the Steinhaus-Johnson-Trotter algorithm, or SJT, which generates all possible orderings of a list by only ever making adjacent swaps.
Which is key. It's not randomly jumping around.
Right, so instead of shuffling the whole deck, you're just swapping two cards that are physically right next to each other. The SJT mechanism works by essentially weaving elements through the list.
Yeah, it takes the largest element and swaps it step by step down the line until it hits the end.
And then the next largest element starts weaving its way back through. But, okay, wait, I'm going to play devil's advocate here. I'm stuck on something.
Sure, go ahead.
If I'm writing software and I just need to generate all permutations of a data set, why go through all this trouble? Why can't I just use a standard list generation function? Why do we need a specialized weaving algorithm that restricts us to adjacent swaps or things like the restricted growth strings for sets? It feels like making basic counting unnecessarily complicated.
This raises an important question because you would naturally think standard counting is fine. But that RAM limitation you mentioned at the very beginning, that is exactly why these specialized algorithms had to be invented.
Oh, so it comes back to the memory issue.
Entirely. Standard computational counting requires massive overhead to track historical states. If you use a normal recursive function to generate millions of permutations, the computer is building a massive call stack.
Because it has to keep the broader structure of the list in its working memory to figure out what branch of the tree it needs to explore next.
Yeah, exactly.
Which eats up your computer's RAM in seconds, because it's essentially holding on to the entire history of the generation process.
Right, it's lugging around all this baggage. But the algorithms highlighted in the presentation sidestep that master list entirely. Let's look at the Ehrlich-Hopcroft-Reingold algorithm, the EHR algorithm.
Okay, the EHR algorithm.
It is considered brilliant because it operates with a state requirement of big O of 1.
Right, a $1. And in computer science, an O requirement means the memory needed remains constant, regardless of how huge the data set gets.
Exactly. The EHR algorithm doesn't need to remember the entire history of the branches it just explored. It just maintains a tiny auxiliary array, looks at the immediate current state of the list, and knows exactly which item to swap with the first item to generate the next unique permutation.
Ah, so the strict rules aren't there to make the math harder. They're there to make the memory requirement practically disappear.
That is the core insight. And we see the exact same efficiency in combinations. The presentation details the Eads-McKay algorithm for combinations, which is also really famously known as the homogeneous revolving door method.
The revolving door, I love that. It's such a great visual metaphor for this.
It perfectly describes the physical mechanism of the math, because a combination differs from a permutation in that the order doesn't matter. You're just selecting a specific subset from a larger group.
Right.
The source gives a really concrete example. Finding all combinations for choosing 3 items out of a set of 6. Mathematically, that yields exactly 20 distinct combinations.
Okay, 20 combinations.
The Eads-McKay algorithm cycles through all 20 by ensuring every single step is merely one item leaving the chosen group and one item entering.
Literally a revolving door. You have a room with 3 people in it, chosen from that group of 6. To get the next unique combination, you don't empty the room and pull 3 new people in. One person steps out, one person steps in, the door revolves. And again, it does this entirely based on the current state, without constantly referencing a giant master ledger of who has already been in the room.
Yes.
This relentless pursuit of memory efficiency, this total obsession with constant memory, is exactly what gave mathematicians the tools to tackle one of the most famous open problems in all of combinatorics.
The middle levels conjecture.
Yes.
From 1982 all the way to 2019, this was a massive, unsolved mystery in the math world.
Here's where it gets really interesting. It is the ultimate boss-level problem for algorithmic efficiency. Let's paint a picture of the setup for everyone.
Okay, let's do it.
You have a massive graph constructed out of bit strings. The length of the string is mathematically defined as $2 plus LL1. And the rule is that the string must contain exactly dollars or plus LL1's one.
Right. So if we set $0 to $2, your string is 5 bits long. And every string in your graph has to contain exactly 2 ones or exactly 3 ones.
And when you map out every possible string that fits that specific description, and you connect the strings that differ by exactly 1 bit flip, you get a highly complex bipartite graph.
A huge one. And the challenge that stumped mathematicians for 37 years was this. Is there a Hamilton cycle through these middle levels?
Meaning, can you find a continuous path that visits every single possible bit string in that massive graph exactly once, changing only 1 bit at a time and eventually arriving exactly back where you started?
And nobody could prove if it was possible to find that continuous, unbroken path for every integer of nullars.
Not until 2019, when researchers Gregor, Muetz, and Newman-Paulo finally cracked it. But their real breakthrough wasn't just proving the path existed, it was constructing a totally memoryless gray code to actually navigate it.
They engineered a way to walk the graph without a map.
Right. Let me try a metaphor here to make sure we're clarifying the mechanism. Imagine you are dropped into a maze that has millions of interconnected rooms.
Okay.
To navigate it using a standard algorithm, you would have to carry around a massive heavy map which represents the computer's memory. Every time you enter a new room, you have to unfold this giant map, trace your whole route from the entrance, and figure out which door you haven't opened yet.
And that map gets exponentially heavier and slower to read with every room you enter.
Exactly. But the Newton-Paulo algorithm ditches the map entirely. You walk into a room, you look at the unique physical shape of the room you're currently standing in, and based entirely on that immediate geometry, you know exactly which door to take next.
You don't need to remember the thousands of rooms you've already visited.
Not at all.
That gets right to the heart of the mechanism. But how does an algorithm look at the quote-unquote shape of a bit string?
Right. It's just code.
Well, it interprets the sequence of ones and zeros geometrically as something called a Dick path. You can visualize a Dick path as a mountain range. Every time the algorithm sees a 1, it draws a line angling up. Every time it sees a 0, it draws a line angling down.
Oh, so a specific sequence of binary code instantly translates into a specific contour of peaks and valleys.
And that contour dictates the next move. By looking at the immediate slope identifying the specific peaks and valleys of that mountain range, the algorithm knows the only mathematically valid bit to flip next.
It derives its location purely from its immediate geometry.
Exactly. It uses bidirectional pointers and localized tree rotations, which are basically just ways of shifting the hierarchical relationships of the data structure locally without needing to know the global structure.
The performance numbers they achieved by ditching that global map are just staggering. Let's look at the data the source provides for when 1 and all equals 15. The number of vertices or rooms in our maze analogy explodes to over 155 million.
If we connect this to the bigger picture, that's 155 million discrete states that need to be visited exactly once. If a computer had to use standard memory mapping to track its path through 155 million nodes, the call stack would overflow and crash most standard machines almost instantly.
But because this algorithm relies on those localized tree rotations, generating the entire 155 million step cycle takes about 2 minutes.
2 minutes.
And it uses less than 50 megabytes of memory.
It is a profound demonstration of computational leverage. Mapping 155 million states with 50 megabytes of RAM proves that gray code principles are not just theoretical math. They are foundational tools for pushing the limits of computation itself.
But memoryless navigation isn't just for abstract numbers and binary graphs. If you want to see where this actually impacts the daily life of the listener, you have to apply this minimal change logic to physical space. Which brings us to our final evolution, rectangulations.
Right, moving from topological graphs directly into physical geometric space. A rectangulation is simply the process of partitioning a large rectangle into a set of smaller, non-overlapping rectangles using straight, axis-aligned walls that span from one side of a bounding box to another.
Think of looking down at the blueprint of a building. You have a massive square warehouse. You need to divide it into a grid of various smaller rooms using straight walls.
Exactly.
In 2021, researchers Marino and Muessa took this concept and asked, can we cycle through every possible geometric floor plan using the exact same minimal change gray code logic we used for binary strings?
And they proved it was possible by developing specific physical shift operations, which they called jumps, to morph one geometric layout into the next unique layout without starting from scratch. The algorithm relies on three distinct mechanical changes.
Okay, what are the three changes?
First, there are W jumps. This involves taking an internal wall segment and sliding it along a perpendicular wall to a new position.
So just sliding a dividing wall down the hallway, basically.
Right. Then there are S jumps, which involve swapping two adjacent rectangles. You aren't moving the outer boundary of the two rooms, you are simply shifting the internal wall that divides them so their orientations flip.
Okay, got it.
And finally, T jumps, which are these complex, localized transformations involving three adjacent rectangles. It rotates their shared boundaries to create a completely new configuration.
So the system is just smoothly sliding walls, flipping adjacent rooms, and rotating blocks of three, one tiny step at a time. And it does this continuously to eventually display every possible blueprint. Now, why does geometric partitioning matter to you? Why should you care about an algorithm drawing boxes inside of boxes?
Because it's everywhere in tech.
Yes, because this spatial optimization is exactly how VLSI design works for making computer chips, how architects optimize floor plans, and even how software renders tree map data visualizations.
Especially VLSI design, VLSI stands for Very Large Scale Integration. It is the core process of creating integrated circuits by combining millions or even billions of MOS transistors onto a single tiny microchip.
Every microchip inside your smartphone, your laptop, or your car's engine controller is governed by this. Engineers have to fit millions of rectangular components perfectly into a microscopic rectangular space.
And it's not just a matter of making them fit like Tetris blocks.
Right. Certain components generate heat and physically can't be placed next to each other. Certain components need to be wired together with the shortest possible path to reduce latency. To find the optimal layout, the compiler software has to test an absolute ocean of different spatial arrangements.
Which is why the memoryless efficiency is so critical. The scale of spatial arrangements grows super exponentially. The source notes that if you want to divide a space into just 10 generic rectangles, so nully equals 10, there are roughly 10 million possible variations of that layout.
10 million different blueprints for just 10 boxes. That's wild.
But by using the gray code approach of just shifting one wall at a time through W, S, and T jumps, the algorithm avoids the massive memory overhead of standard generation.
Which speeds everything up.
Massively. When combined with standard compiler optimizations like using the -03 flag in C++ wheel, which essentially tells the compiler to aggressively optimize the code for speed, resulting in a 3 to 5 times performance boost, the algorithm can generate and evaluate all 10 million geometric variations in just 5 minutes.
Just 5 minutes. It's an incredible engineering feat. We're looking at a computational strategy that scales almost infinitely, specifically because it refuses to carry baggage. It refuses to hold on to the past.
It just looks at the present state of the chip layout, makes one tiny localized wall adjustment, evaluates it, and moves forward.
That principle is really the grand unifying theme of the entire presentation. From Frank Gray trying to prevent voltage spikes in 1953, to weaving permutations with adjacent swaps, to solving the 40-year middle levels conjecture, and finally organizing the physical transistors on modern microchips.
The underlying magic is always the memoryless gray code.
Yeah.
It is the mathematical realization that whether it's binary strings or geometric layouts, you can achieve immense, unimaginable scale with algorithms that possess a step complexity of big O of 1 and a total state space of big O of n.
So what does this all mean? It gives the system the power to change exactly one element, seamlessly, moving forward without ever breaking the machine under the weight of its own memory. True elegance in computer science, and maybe in complex problem solving in general, isn't about brute force.
No, not at all.
It's not about having the biggest bulldozer or the most RAM. It is about doing the absolute most with the absolute least amount of effort and memory. It's realizing that sometimes the fastest way to travel through millions of vast possibilities is to narrow your focus entirely to the single smallest step right in front of you.
It is a profound shift in how we approach complexity. And the application section of the source material hints that this efficiency isn't just a quirk of computer engineering. It appears in fields far beyond silicon chips.
Yeah, the source lists applications like advanced error detection, complex cryptography, and genetic algorithms. And that last one is what I really want to leave you with today.
It's a great point to end on.
Genetic algorithms use these exact minimal change principles to model mutation in space exploration and biology. If biological mutation, the very way DNA evolves and adapts over millions of years, and the most advanced data encryption systems on Earth both rely on efficiently exploring vast, near infinite possibilities through minimal, single step changes without retaining a massive global memory, it raises a fascinating question.
A really deep one.
Could nature and the universe itself be operating on a giant memoryless gray code? Is the fabric of reality just optimizing its state one tiny, elegant bit flip at a time?
It definitely forces you to rethink how nature processes information. We expend so much energy building massive, power hungry machines to calculate the world, but the fundamental mechanics of the universe might just be incredibly memory efficient.
Something to mull over the next time you see a computer handle a massive, complex task without breaking a sweat.
Yeah.
It isn't always brute force pushing through the data. Sometimes it's just turning one dial exactly one notch at exactly the right time.